Part 1. The Divine and the Abstract. Before the word, before the alphabet, there was the count. Not a language of gods, but a language of survival. A calm, deep voice begins, speaking over the visual of a dimly lit, rough-hewn cave entrance near a small, controlled fire. An ancient man, a figure of authority and experience, dressed in simple, practical animal hides appropriate for the Upper Paleolithic era. 30,000 BCE, sits holding a fragment of bone. The piece is carefully marked with deeply carved notches scoring its surface, strikingly similar to the archaeological find known as the Ishango bone or other ancient tally sticks, evidence of deliberate, recorded, numerical thinking, a foundational step toward quantification. The man points a crude implement at the marks, demonstrating the earliest form of systematic, organized recording. A younger apprentice, observant and focused, their appearance also entirely appropriate for early Homo sapiens, sits watching and reaches out to trace the distinct groupings of the markings, noticing the latent patterns embedded in the raw material, subconsciously absorbing the rhythm of arithmetic. Our early ancestors looked up at the moon, meticulously tracking its slow decay and predictable cycles of disappearance, and return a lunar calendar etched in bone. They looked out at the herd, carefully counting the animals that meant the critical difference between survival and famine. The first mathematics was a fundamental, yet inherently sacred, inventory. A deliberate mark for the passage of 1 day, then 2 days, then 3. A precise notch to account for 1 successful hunt, 2 kills, 3. These primitive numerical recordings were not conceived as symbols of a grand cosmic theory, but functioned as essential, pragmatic anchors in a chaotic, unpredictable world. It was in this cold, raw calculation of how many resources were available and how long they would last that the first truly abstract thought began to solidify, separating quantity from the object counted. Number emerged as a foundational, indispensable tool, a simple, practical necessity born from the overwhelming pressures of existence and the need for prediction. The necessity for mathematical precision intensified exponentially as organized civilizations began to arise. Along the fertile banks of the Nile, the annual, destructive flooding required sophisticated, repeatable surveying and planar geometry to constantly redefine property boundaries and ensure fair taxation across the region. Simultaneously, high upon the elevated Mesopotamian ziggurats, complex number systems tracked the precise movements of celestial bodies, used to forecast seasons, predict agricultural output, and even to interpret omens and fate through early forms of astrology. Mathematical knowledge was a potent political power, but its primary function remained practical, grounded in serving commerce, monumental construction, and accurate calendar. Keeping it was a highly effective tool for managing terrestrial affairs. But then, the practical tool was suddenly seized, reinterpreted, and wielded by a profound mystic philosophy. The scene shifts dramatically to a sunlit, colonnaded courtyard in ancient Greece, around the 6th century BCE in the southern Italian colony of Croton, the intellectual setting where the Pythagorean school flourished in the Archaic period. Olive trees provide dappled shade. Pythagoras, a pivotal figure of classical antiquity, appears mid-aged, serious, and deeply bearded, draped in a simple white linen himation, robe, an accurate representation of scholarly dress from that time. He stands over a monochord, a single-stringed instrument carefully marked with precise mathematical divisions on the wood, a physical demonstration of his core belief. Attentive disciples, also dressed in simple robes appropriate for the time, sit clustered around him on stone benches, hanging on his every word. The Ionian philosopher fundamentally altered the perception of number. He did not see numbers as mere functional quantities used for transactional accounting. He saw them as the immutable essences of reality itself. He sought not simply to count physical things, but to fully understand the divine, pre-existing blueprint they inherently concealed. He tells his students that the vast cosmos is not chaos, it is pure, absolute mathematical harmony. He demonstrates this principle, generating precise, controlled sound from the monochord. He explains that the strings that produce a perfect fifth, the most pleasing and consonant musical interval to the human ear, are determined by nothing more than a vibration dictated by the simple, immutable ratio of 3 to 2, 3 to 2. The octave, the sound of perfect return and unity, is defined precisely by 2 to 1, 2 to 1. This discovery of numerical regularity in music was nothing short of revolutionary. He realized that the identical, simple ratios that governed and pleased the ear could be discovered and replicated in the vast, silent, predictable motions of the planets, the music of the spheres, the perfect symmetry of a crystal structure, and the inherent geometry of a right-angled triangle. Numbers were immediately elevated to the language of the gods. They constituted a secret, fundamental code that, once fully deciphered through rigorous study and spiritual devotion, would not just describe the universe, but reveal its very soul. The geometric theorem that now universally bears his name, A, 2 plus B, 2 equals C, 2, was far more than a simple geometric rule for him. It was tangible, irrefutable proof of an underlying cosmic order and perfection, confirming that the area of the square built upon the shorter sides was intrinsically and perfectly linked to the area of the square built upon the longest side. One disciple points towards a large tablet etched with the precise diagram of the Pythagorean theorem, solidifying the idea that this was truth revealed, not invented. The conviction of the Pythagoreans was uncompromisingly absolute. All is number. This was not mathematics conceived as a practical tool for empirical science. It was mathematics held as religion, a spiritual and intellectual quest for cosmic unity and purification, with the ultimate structure being the tetractys, the sacred triangular number of 10, which represented the fundamental organization of space, time, and the musical spheres of the cosmos. Their belief was in mathematical Platonism before Plato himself codified it. For centuries following, the powerful Pythagorean conviction that the laws of mathematics were fundamentally woven into the very fabric of creation served as a powerful engine for philosophical and scientific inquiry across various cultures. But the central focus gradually began to shift from mysticism to mechanics. The scene changes dramatically to a study during the Enlightenment period, around the 17th century in Western Europe. It is a dimly lit, high-ceilinged room, meticulously cluttered with scientific instruments like early brass telescopes, astrolabes, and terrestrial globes, along with heavy, leather-bound books, reflecting the rise of empirical observation. A single window casts a bright, revealing shaft of light onto a sturdy wooden desk. A philosopher, dressed in the formal, dark attire of the period, a simple doublet and breeches, is sitting intensely at the desk, his focus entirely intellectual. With the rapid acceleration of the Renaissance and the scientific revolution, mathematics underwent a significant, critical transformation, moving from a divine, static revelation into the ultimate, dynamic, abstract tool specifically designed for describing, modeling, and manipulating the observed physical world with unprecedented accuracy. The philosopher is shown writing furiously on a large sheet of paper, developing and detailing the principles of a Cartesian coordinate system, marking the critical point where geometry and algebra were fundamentally connected for the first time. This was the genius of René Descartes, who successfully married these two great pillars, creating the system of coordinates. Suddenly, any point in space, any physical shape, could be described not by a mystical, perfect ratio or an ideal form, but by an ordered, precise pair of numbers, x, y. The physical world, which had often seemed subjective and messy since antiquity, was now definitively quantifiable, objective, and perfectly mappable onto a rational grid. The scene shifts slightly to show the philosopher sketching the trajectory of a falling apple, illustrating the force of gravity, leading directly to the visualization of an orbital path. He is writing an early differential equation, surrounded by his instruments. He is, of course, Sir Isaac Newton. He did not simply describe motion or its observed effect. He invented a whole new abstract language, calculus, both integral and differential explicitly to predict it precisely. The exact rate of change, the instantaneous velocity of an object, the complex curved path of a planet's orbit, all became solvable, predictable, and manageable problems through the immense power of infinitesimals and limits. The resulting equations were rigorous, predictable, and entirely devoid of classical mysticism or spiritual interpretation. They functioned as a powerful, abstract lens, allowing humanity to look beyond the surface of the stars and see the cold, hard, universal mechanics of gravity in action. Math was no longer merely the language of the gods. It was the indisputable master key to the clockwork universe, a powerful tool devised by the human mind. Just as humanity settled into the certainty that the mechanical universe was fully understood, a quiet clerk in a Swiss office unexpectedly rewrote the entire master key. The scene is a simple, slightly cluttered office in the early 20th century, specifically between 1905 and 1915, potentially the Swiss Patent Office or an early university setting, capturing the ambience of that turn-of-the-century period. Albert Einstein, young and in his early years of world-changing discovery, wears a simple suit appropriate for the period. He stands next to a blackboard completely covered with complex but profoundly elegant mathematical notation, prominently featuring the famous E equals mc, 2. He had no new empirical data to drive his initial conclusions. Instead, he started from thought experiments and first principles. He had a pencil, paper, and a profound, almost Pythagorean, faith in the beauty and internal consistency of mathematics. He recognized that the numbers describing space and time were not fixed, static quantities, as Newton had presumed. They were fundamentally elastic and relative. Space itself, he postulated, was a dynamic, four-dimensional structure inextricably interwoven with time. Space-time, the mathematics of special relativity, centered on E equals mc2, was an almost shockingly simple yet powerful tool that revealed the fundamental interchangeability of energy and mass, fundamentally altering the worldview in a manner never before seen. The scene shifts to an abstract visualization. Einstein is now seen near a vast representation of a curved grid, illustrating the concept of general relativity. He is looking thoughtfully at a geometrical diagram depicting space-time curvature caused by mass and energy. His voice is heard, calm and thoughtful, stating a philosophical truth. The most incomprehensible thing about the world is that it is comprehensible. General relativity, fully described by the dense tensor equations g, mu, nu, plus lambda, g, mu, nu, equals frac 8 pi, g, c, 4, t, mu, nu, was mathematics at its most powerful and abstract peak, a purely intellectual creation. It was a tool so overwhelmingly powerful it did not just describe gravity, it dictated that gravity was not a distant force, but an inherent curvature in the geometric structure of the cosmos itself, directly caused by the presence of mass and energy. The pure elegance and inherent symmetry of the equations suggested a critical, modern return to the Pythagorean conviction. The universe must be mathematically beautiful, and therefore, the most elegant mathematical description must be true. The ultimate abstraction, for the first time since the Greeks, was clearly the ultimate reality. Part 2. The Quest for Unity and the Ultimate Code. The immediate, groundbreaking success of Einstein's mathematical prophecy inadvertently opened a fundamental, persistent schism in modern physics that defines the current era. The scene shifts to the interior of a massive, technologically advanced particle physics laboratory, such as a major section of CERN, emphasizing the overwhelming scale of the machinery and the complexity of the data acquisition systems. The space is dominated by massive, complex detectors and machinery, with glowing monitor screens displaying complex dynamic data visualizations. The lighting is intensely artificial and precise. Modern physics is currently split into two distinct, incompatible domains. The classical, graceful curve of general relativity perfectly describes the very large, stars, galaxies, cosmology, while the probabilistic, entirely different world of quantum mechanics governs the very small, particles, subatomic forces. Quantum mechanics, described by the abstract mathematical language of Heisenberg's uncertainty principle and the iconic wave function defined by Schrödinger's equation, I, h bar, frac, partial t, psi equals hat, h, psi, completely abandons the deterministic certainty that was the cherished hallmark of classical physics. It trades absolute knowledge for probability distributions. A particle physicist is looking intently at data on a screen and gestures toward an image of particle collision results, colorful, abstract tracks of energy radiating away from a central point, a visualization of fundamental, fleeting interactions. Quantum mechanics is the ultimate mathematical tool for rigorous prediction and engineering success, underpinning all modern electronics and chemistry. Yet philosophically, it speaks of reality as fundamentally unpredictable at the core, a wave of potential probability that only instantly collapses into a definite particle state upon the act of observation. It is a stunningly effective calculation tool, but it fails completely to give us the satisfying, concrete, deterministic image of reality that the earliest philosophers like Pythagoras, or even Einstein himself, craved. It functions as an instruction manual for the universe that leaves the ultimate why permanently and deliberately blank. A theorist, standing nearby, holds a complex printout of highly theoretical equations, pointing to a section of a complicated formula, illustrating the immense difficulty of integrating the two perfect but contradictory mathematical descriptions of reality. This inability to unite the physics of the large and the small is the current state of modern physics. We possess two distinct, beautiful, and empirically verified mathematical tools, and yet they fundamentally contradict each other at the deepest level of existence, especially near singularities like the Big Bang or the center of a black hole. We are standing on the precipice of a final, necessary unification, where the true singular language of the entire universe must finally be found. We are engaged in a monumental effort seeking the single, overarching mathematical structure, the elusive theory of everything. The ultimate search for unity takes us deep into the most abstract, conceptually challenging mathematical structures ever conceived. The scene changes, becoming conceptual and futuristic. A clean, minimalist conceptual space, entirely divorced from the clutter of a physical lab. Holographic projections of complex, multidimensional shapes and the visualization of minute, vibrating strings are visible everywhere, indicating highly advanced computation. The atmosphere is quiet, contemplative, and focused entirely on pure abstraction. Enter string theory, the dominant contender for unification, which posits that the fundamental particles, electrons, quarks, photons, are not zero-dimensional points, but tiny, one-dimensional, vibrating filaments, the strings. The entire observable universe, gravity, matter, all known forces and energy, is simply the resulting vibrational harmonics of these strings, operating within a highly complex space of 10 or 11 spatial dimensions, most of which are hidden from our everyday perception. A futurist, a theoretical physicist, or mathematician walks past a projection of a Calabi-Yau manifold, a complex, symmetrical, six-dimensional shape that represents the hidden extra dimensions curled up and existing at every single point in our observed three-dimensional space. The mathematics required to construct this theory is staggering. It demands the existence of concepts like supersymmetry and the eventual emergence of M-theory to be fully consistent and eliminate mathematical inconsistencies, anomalies. Crucially, these theories are not yet directly testable with current technology, but they are relentlessly driven forward by a profound, almost mystical belief in mathematical elegance and necessity, a principle guiding the whole field. If the equations are ugly or inconsistent, the theory must be wrong. The underlying philosophical axiom is clear. If the mathematics used to construct the theory is internally beautiful, fully coherent, and logically consistent, then it must, by the necessity of logic, somehow describe the genuine reality. This effort represents the ultimate synthesis of the two worldviews, marrying the abstract, invented tool with the pre-existing divine language. the futurist's voice is heard, reflective and hopeful, stating a profound realization. We are not merely finding the gods' language, we are discovering the language the gods used to write the universe in the first place. String theory eloquently suggests a cosmic symphony, a massive, intricate Pythagorean dream realized not through simple ratios like 3:2, but through the infinitely complex, resonant frequencies of these minute, one-dimensional strings. The difference between an electron and a photon is mathematically reduced to simply the difference in the specific mode in which its underlying string vibrates. The original dictum, all is number, is elegantly refined and expanded. All is not number itself, but vibration, which is, fundamentally, a complex, organized function of number. So, the age-old, cyclical question remains open, defining the human condition. Is mathematics the language of the gods, an objective, eternal truth existing outside human consciousness, waiting only to be discovered? Or is it a brilliant, powerful human tool, a magnificent, adaptive abstraction invented by the mind to make comprehensible our sensory observations of the messy physical world? The scene shifts one last time to a vast, open celestial observatory or dome, overlooking a beautiful, complex visualization of the entire cosmos based on a presumed unified theory. The setting feels both ancient in its pursuit of truth and futuristic in its technological scope. An elderly scholar, a highly reflective figure, is looking out at the magnificent, illuminated celestial view. The practical utility of the tool is absolutely undeniable and proven. Mathematics has accurately predicted the existence and properties of black holes decades before they were observed, guided the discovery of new fundamental particles, and provided the exact navigation to put humanity on the moon. Yet, the persistent, almost supernatural effectiveness of purely abstract mathematical concepts, how a theoretical thought experiment like non-Euclidean geometry, considered mathematical play when invented, can suddenly become the perfect, accurate description of the relativistic physics of gravity, suggests something far deeper than mere utility or coincidence. The Nobel laureate Eugene Wigner famously termed this phenomenon the unreasonable effectiveness of mathematics in the natural sciences, a feeling that the human mind has tapped into an external, fundamental structure. The scholar turns from the breathtaking cosmic view to look directly at the viewer, speaking with calm and final conviction. Perhaps the distinction between tool and language is fundamentally flawed and unnecessary. Perhaps mathematics is, in essence, the human mind's only available way to perceive, interact with, and articulate the ultimate structure of reality. The tool, in this view, is the language. By diligently building the most perfectly consistent, logically sound abstraction possible, humanity is forced, by the immutable laws of logic and structure itself, to describe the actual, inherent structure of existence. This journey of discovery, spanning millennia, from the single, simple, essential notch on a Paleolithic bone to the complex 10-dimensional harmonies of the theoretical strings, demonstrates that mathematics remains our most profound, enduring, and successful connection to the universal structure. It is the language we speak to the cosmos in our inquiry, and the language the universe speaks back through in its immutable, elegant laws. The critical, eternal conversation continues, and the final word, like the most profound and encompassing theorem, has yet to be fully written by either man or God.